So in our discussion of how oxygen and carbon dioxide are transported through the blood and how exchanges occur between the alveolus and the blood and between the blood and the tissues, we have to keep in mind that gases move from areas of high to low partial pressure and that they move by simple diffusion. So in this drawing here we have an alveolus, we have our arterial blood, we have a working cell, and we have our venous blood here. We're skipping the circuit through the heart for simplicity. So let's start out with identifying what the partial pressures of gases are in our different places. So in the atmosphere, the partial pressure of oxygen is typically about 155 millimeters of mercury. Depends on your altitude. This is typical of sea level and obviously will vary a little bit depending on what the humidity is. And the typical partial pressure of CO2 is really low. It's about 0.3 millimeters of mercury. Now, these partial pressures are not the same in your alveolar space. The partial pressure of oxygen in your alveoli is only about 100 millimeters of mercury. And I'm going to leave off the millimeters of mercury on the rest of these for simplicity, but keep in mind these units, millimeters of mercury, are the same throughout this diagram. And the partial pressure of CO2 in your alveolar space is typically about 40 millimeters of mercury. So why are these different? Well, remember earlier when we were talking about alveolar minute volume, and we said you had to subtract residual volume from your calculation of tidal volume, and that's because there's always some residual air left in your lungs. No matter how hard you try to breathe all of the air out of your lungs, there's always that little bit of stale air or residual volume left in there that dilutes the fresh air coming in. So you have a bit less oxygen than you would in the atmosphere and quite a bit more CO2 than you would in the atmosphere. Okay, let's look at the partial pressures of oxygen and CO2 around a working cell. So this is a drawing for a person who's, maybe just sitting around, kind of at rest, but obviously lots of your cells are still working, the sodium, potassium, ATPase, and pumping your blood around your body. So it's not an exercising person, but a resting person. But of course, those cells are still working. So typically the partial pressure of oxygen in a cell would be less than or equal to 40 millimeters of mercury. And the partial pressure of CO2 is typically going to be greater than or equal to about 46. Now, let's start this circuit by looking at the venous blood that's returning to the heart. So the partial pressure of oxygen in the venous blood returning to the heart is going to be about 40 millimeters of mercury, and the partial pressure of CO2 is going to be about 46, and you'll see where these numbers came from in a minute. And so this blood is moving through the pulmonary capillaries. Now, remember we said that gases move from areas of high to low partial pressure, and these are in really close proximity with each other and can diffuse right across these membranes. So notice that we've now got a partial pressure gradient for oxygen. It's at 100 in the alveolar space and it's at 40 in the blood. That means it's going to diffuse into the blood until it reaches equilibrium. So you're breathing the whole time, so you're constantly bringing fresh air into your alveolar space and bringing the partial pressure of oxygen up to 100. And so when these gases reach diffusional equilibrium, that will happen when the partial pressure of oxygen reaches 100 in the blood. Similarly, the same thing will happen with carbon dioxide, except the partial pressure gradient for CO2 goes in the other direction. Notice that it's about 46 in this venous blood that's moving into the pulmonary capillaries, and it's about 40 in the alveolar space. So CO2 will diffuse out. And again, it will diffuse out until it reaches diffusional equilibrium with the alveoli, and we will end up with a PCO2 equals 40. And this oxygen enriched and CO2 depleted blood will circulate and enter the capillary beds. So this is a capillary bed right in this area. This is a capillary bed. And so it'll enter these capillary beds with a partial pressure of oxygen, still 100, and a partial pressure of CO2, still 40. And the same thing happens at the capillary beds around the tissues. We've got a partial pressure gradient for oxygen. Oxygen's at 100 in this arterial blood that entered these systemic capillaries, and it's less than or equal to 40 in the cells. So oxygen will diffuse out until it reaches diffusional equilibrium, which means it will get to a partial pressure of 40. So PO2 is 40. And similarly, CO2, again, will follow its partial pressure gradient. There's more around the cells than there is in the blood, because it's at 46 in the cells and 40 in the blood, and it will diffuse into the blood until it reaches a partial pressure of 46. And that's where we got those numbers for that venous blood that returned to the heart and then was sent to the pulmonary capillaries. So these are the normal partial pressures for oxygen. So normally, if you are healthy and you're at a normal altitude, you should always have a partial pressure of 100 millimeters of mercury of oxygen in your arterial blood. And there's lots of reasons why you might not have the normal amount of oxygen in your blood. So let's think about some possible reasons why you might have a low partial pressure of oxygen in your blood. So let me just draw a little alveolus here, and we'll put some blood nearby. Here's some blood. And we know that the partial pressure of oxygen in the atmosphere is normally about 155 millimeters of mercury, and normally about 100 in the alveolar space. So the most obvious reason maybe would be that there's low partial pressure of oxygen in the atmosphere. So low PO2 in the atmosphere. So that could maybe happen at high altitude, for example, or if you're trapped in an enclosed space, which we're not going to think about that. So that could be one obvious reason. If you have low oxygen in the atmosphere, then you'll have, like, let's say you start climbing to altitude and it's only 100 millimeters of mercury in the atmosphere, then you might only have 60 millimeters of mercury of oxygen in your alveolar space. So not very much is going to be able to diffuse into your blood. Well, maybe you're at normal atmospheric partial pressures of oxygen, but maybe for some reason you have a low partial pressure of oxygen in the alveoli. So this could happen if, for example, you are someone who has asthma and you have some bronchoconstriction going on. So maybe up here in your bronchioles, you have inflammation and bronchoconstriction, so you have less oxygen, or less air rather, able to move through the bronchioles. So for example, if you have asthma with its associated bronchoconstriction, or maybe you're choking on something and you have an obstruction. We could draw, oh no, an obstruction here. And that would reduce the partial pressure of oxygen in the alveoli, because you would be having less ventilation happening. And in fact, you could have a low ventilation rate too. That would be another reason. If, for example, you were on narcotics, and that happens often to people who are on narcotics. They will have a lower ventilation rate, which means they have a lower partial pressure of oxygen in their alveoli. Well, maybe you are at a normal atmospheric pressure and you're ventilating your lungs normally, but you still have a low partial pressure of oxygen in your blood. Maybe you have a barrier to diffusion. So a barrier to diffusion. Remember that oxygen has to diffuse across the type 2 alveolar cells, type 1 alveolar cells rather, across the endothelial cells of the blood vessels into the blood. And so if you, for example, have bronchitis or pneumonia, and let's say you have fluid here, or fluid in your lungs, and now oxygen has to pass through this wider diffusion barrier, then less oxygen is going to be able to diffuse into the blood. And so people who, if you've ever had pneumonia, they probably checked your oxygen saturation, and it may have been lower. So we could have edema or swelling. So, for example, remember we talked about congestive heart failure. That could create that edema, or mucus if you have a respiratory infection like pneumonia or bronchitis. The last thing is maybe everything is normal. There's a normal pressure of oxygen in the atmosphere. You're ventilating your lungs normally. There's no barrier to diffusion, yet you still have a low partial pressure of oxygen in your blood. Well, remember how oxygen is carried on red blood cells that are full of hemoglobin. Well, if you have low amounts of hemoglobin in your blood, so we have hemoglobin in there, then that would be another problem and would reduce the amount of oxygen that you can carry. Because remember, oxygen's not very soluble in water. So if we have a low concentration of hemoglobin in the blood, plasma carries about 3 mils of oxygen per liter of blood. That's not very much. It's not enough to keep you alive for sure. Hemoglobin carries about 197 mils of oxygen per liter of blood. So your normal oxygen carrying capacity is about 200 mils O2 per liter of blood. And so if you have less hemoglobin, and HB equals hemoglobin, so if you have less hemoglobin, then you're going to be able to carry far less oxygen, because as the oxygen diffuses in, it binds to hemoglobin and is transported around. And that's actually the next thing we're going to talk about, is how hemoglobin carries oxygen. So the condition, if you have low hemoglobin in your blood, we call this anemia. And there's lots of different kinds of anemia. You could have iron deficiency anemia. If you don't have enough iron in your diet, you don't make enough hemoglobin and enough red blood cells. But there's lots of other forms of anemia that involve mutations in the gene coding for hemoglobin, and all of those types of anemia will affect the oxygen carrying capacity of blood. So tune in for the next video on the oxygen hemoglobin saturation curve.